let's solve a couple exponential equations here. So maybe we could really quick remember what our goal was here. So first we wanted to, if we could, we wanted to rewrite both sides with the same base so that we could pull the trick where if we have the same base on both sides, then we can say that the exponents have to be equal, right? So if we can, we want to pull that trick. But if we can't, well, we're going to have to do something different. We're going to have to say maybe if I've got two numbers that are the same, I can say that the natural log of those numbers would have to be the same. And if we had that, well, then we can apply that power rule. But let's see that as it comes, right? So our first strategy is going to be rewriting these things with the same base, so we can just say the exponents are equal. So this first one here, we want to rewrite these objects. If we can, we want to use the same base on both sides. So this is a 7, right? I mean, clearly it's a 7. We're not going to be able to rewrite 7 with a base of 3. So that's going to maybe be problematic for us. But let's try to maybe first rewrite this with one base. So I know that 9, that's 3 squared, right? And that's 3 to the x. Nothing changed on that side. So I've got the same base now. And if I multiply two numbers together, they've got the same base, different exponents. We add the exponents, right? So this is 3 to the 2 plus x equals 7 to the 2x. All right, so now these things have the exponent is, each base is isolated on each side, and they're equal, right? So if they were the same base, like if both these things were 3 or if both of them were 7, we could just say, hey, the exponents have to be equal because these things are 1 to 1. Well, we don't have that, but what we do have is that the sides are equal, so that means that their natural logs also have to be equal. You know, technically we can use the same base no matter what the base is. As long as it's a legal base, we can use it as long as it's bigger than 0, not 1. But usually we use a natural log because we have to write less. So essentially what we're going to do is we're just going to apply a natural log to both sides. And you can use the same base you can use any base you want. But conveniently, we usually use natural log because that's, again, writing less. Okay, so now we have that natural log of this thing is equal to natural log of this thing. Well, that's convenient for us because now we can use that power rule and we can get our exponents out of that position. We can rewrite these as factors, right? So I'm going to have 2 plus x is now a factor in front of this natural log. And also 2x is a factor in front of this natural log. Okay, so now we can't really lose sight of what we want to do. We want to solve for x, right? We want to get our x's on the same side. So the first thing we're going to do, or not the first thing, but the next thing we're going to do is we're going to distribute this because we want to get that x out of the parentheses. So I've got 2 times natural log 3 plus x natural log 3, right? All we did in that step was we just distributed that term to both of those. Okay, that didn't go anywhere. So now we want to get all these x terms by themselves, right? So maybe we could subtract that from both sides, or maybe we want to get our x terms on the other side. So let's do that. Let's have our x terms on the left side. So I got x natural log 3 minus 2x natural log 7, and then let's get that on the other side. Okay, so really we just subtracted this guy from both sides, and we subtracted this guy from both sides. Okay, now we can factor out our x. So we got x times what would be left would be natural log 3 minus 2 natural log 7. And now we're home free, right? Because this thing is just some number. This thing is just some number. And we've got our variable isolated. So we can then just divide by this, right? We got x times this junk. So we're going to divide to get x alone. So x is going to be -2 natural log 3 over this thing. So part of our difficulty in this is that's a separate problem. So part of our difficulty in this section and in expressing our answers is going to be the fact that we can write this thing in a whole bunch of different ways. If I really wanted to, I could use that power rule again in reverse and tack this up there as an exponent. I could use the quotient rule in reverse to write this as a quotient, right, after I use the power rule. But be aware that sometimes our answer is going to look kind of ugly. And we can absolutely rewrite these things in a different way if we want to. But I'm pretty confident that WebAssign is going to take that as an answer. So we might want to simplify it, but be aware, right? We can write these things in a bunch of different ways. Okay, let's do the next one. So we want to do this guy. Okay. So we want to isolate, our first goal is to isolate the exponent stuff. And if we can, we want to rewrite it with the same base. These problems here are going to be probably especially difficult for you because I want to combine that 6, but that's not going to combine with that term. We're going to have to do something else. So we can use a slightly different strategy that we've probably seen before, but maybe not in this context. If we want to let's get everything on one side. So I can have 25 to the x minus 5 to the x minus 6 equals 0. All right, everything's on one side. If I wanted to go and try to start combining these things in particular, I'd probably want to write them with the same base, right? I know that 25 is 5 squared, so I can write 5 squared to the x minus 5x minus 6 equals 0. Okay, so if I really wanted to, I could write that as 5x squared, couldn't I? And now hopefully we can see where this is going. If we now notice that this is a quadratic form, that's super convenient for us, right? We've got a variable part and then the square of that variable part. So this has quadratic form, right? So if we let maybe another variable a equal 5 to the x, then we can rewrite this thing as a squared minus a minus 6 equals 0. So that is super convenient because now we can factor that, right? That'd be x minus 3x plus 2. And, or excuse me, x, that's a, right? We did the substitution, excuse me, that's an a. So now we can conclude that a minus 3 equals 0 or a plus 2 equals 0. I see that I'm running off the page there. So maybe we can come underneath. So a minus 3 equals 0. That tells us that a is 3 or a is -2. But we got to remind ourselves we weren't looking for a, we were looking for x, right? So going back to what we did for our substitution, we just put an a in place of 5 to the x. So we're going to go ahead and substitute that back. So I got 5 to the x equals a, 3, or 5 to the x equals -2. Okay, so either 5 to the x is 3, or 5 to the x is negative 2. So we can recall a property of these exponentials, and we can just throw this one out right away, right? 5 to any power, no matter what power this is, this object is always going to be positive. So we can throw that one out because that's never, ever, ever going to be true, right? 5 to any power is never going to be negative. It's always going to be, well, positive. So that one we throw that out. And this guy, we can do this in a couple of different ways. We could either set the natural logs of these things equal, or we could just rewrite this with logarithms. So if we rewrote the exponential statement with a logarithm, we could rewrite that as x is the power I raised 5 to get 3. And then we're done. Of course, we can definitely do the other thing that we just did with that last problem, right? We could take a natural log of both sides, use the power rule and divide, and that's absolutely true. But why do the hard thing when I can do the easy thing? So do the easy thing, right? Okay, so that was that one. Great. And now I see that I'm gonna run out of room, so I'm just gonna write this on a separate sheet here. So we want to solve e to the x minus e to the negative x over 2 equal 5. So our first instinct here is probably to panic, right? Because there's a whole bunch of stuff going on here. There's a lot of letters and numbers flying around. But I would urge you to not panic. We want to just do the same thing we always do, right? So we have an equation here. We want to solve it. So if we have fractions, we usually want to do the same thing every time we have fractions, and that is to, well, get rid of the fractions. So if I multiply both sides here by 2, that fraction is going to go away, right? So I can rewrite this as e to the x minus e to the negative x equals 5 times 2 is 10. Okay. Well, we still have a fraction here, don't we? If we rewrote that, I'd have e to the x minus 1 over e to the x equals 10. Because that's what a negative exponent does. Remember that? So if I wanted to further go on getting rid of my fractions, I would go ahead and multiply both sides by the least common denominator, which is e to the x. And we can do that. So now we have distribute, right? E to the x times e to the x. Then this one we distribute. So e to the x times e to the x. This is e to the x squared. And then we've got e to the x times negative 1 over e to the x. That's just going to be negative 1. And then here we've got 10 times e to the x. Okay, so now maybe we can see the writing on the wall here a little bit. We can see that this is very, very similar to the last problem we just did. And we can, notice that it has quadratic form, right? So we can put 10 e to the x on this other side. We've got e to the x squared minus 10 e to the x minus 1 equals 0. And then we can probably see that this is going to be kind of messy. So if we let e to the x be some other variable, maybe a, we can rewrite this as a squared minus 10a minus 1 equals 0. And now, hey, it's got quadratic form, and we can apply the nice quadratic formula. So I can say here that a would need to be, well, we're just going to apply the quadratic formula, right? So negative b was 10 minus the square root of b squared would be 100 minus 4 times a times c divided by 2 times a, which would be 1. Okay, so simplifying that, we would have 10 plus or minus, I forgot the plus or minus part, plus or minus the square root of 104 over 2. Okay, and we can simplify that, right? This is 10 plus or minus 104 is divisible by 4, right? and it goes in there 21 times. No, it doesn't, 26 times. So that's 2 times the square root of 26, or 2. So that's 5 plus or minus square root of 26. Okay, great. So that's what A was. But we didn't care about A. We cared about e to the x, right? We wanted to know what x was. So we can go ahead and substitute back. We can say e to the x now is equal to 5 plus or minus square root of 26. Okay, and now I've got my exponential function here is isolated, and we would just do what we would do there. We could either rewrite this with rewrite this with logarithms, or we could take the natural log of both sides, which would be probably more convenient for us. At least we're going to have to write less, right? Because I know that natural log of e to the x, we're finding the power that we raise e to get e to the x. That's just x. And then that's going to be natural log of this stuff. So for this one, we found 2 solutions, right? So our x is alone, and we have found 2 solutions. So we want to know which one we want. We know from our basic properties of these logarithms, whatever is in this position here needs to be bigger than 0, right? We can write that. So we have to have this thing is bigger than 0, so we can discard the negative solution, right? The negative solution is going to be, well, 5 minus square root of 26 is going to be a negative number, so we got to get rid of that one. We only want the positive. So we're going to say x is natural log of the positive one. And we're done.